Okay, we can continue with the proof of the channel coding theorem. So I said achievability or direct part. We want to prove that for any rate R strictly less than C, where C is the maximum of the mutual information, there exists a sequence of Rn codes with vanishing probability of error. So here we introduce a very powerful idea, uh, which is called random coding. Random coding, in fact, is an idea also due originally to Shannon, uh, and it works as follows. Constructing explicitly these codes is a very difficult problem. So instead of constructing deterministically this family of codes, we can simply consider an ensemble of randomly generated codes, average over this ensemble, analyze the average probability of error averaged over the ensemble of codes, and then if this average probability of error goes to 0, it means that there exists at least one sequence of codes that behave better than average, and this proves existence, although in a non-constructive way. So the idea is, let's consider an ensemble of codes, which means consider a probability distribution over X, call it Px, and then generate a random codebook. Simply generate an array with 2 to the n r rows and n columns, so as the big table of code words, simply by filling the table, generating symbols in an IID fashion according to probability Px. For example, if I have a binary channel and I take Px to be a uniform, I will have random zeros and ones. So I have this big table. It will be a big binary array with random zeros and ones. Every row is a code word. So the encoding function is just indexing row by row with the messages. And the decoding here is, well, it's something that we can pick. The decoding function can be defined as we want, and so here we choose a particular decoding function that allows the proof. It's up to us in an achievability proof constructing a decoding algorithm that on one hand has to be simple enough to be analyzed, on the other hand has to be good enough to prove achievability of rate up to capacity. So this requires a little bit of intuition. In this case, as in many cases in information theory, we consider what is called the joint typicality decoder. That's again a non-practical algorithm, but it's a conceptual algorithm that works as follows. Given the received sequence Y, then the decoder will pick the message m hat if this is the unique index such that the corresponding code word x of m hat and y are jointly typical. Otherwise, if either there is no code word that is jointly typical with the output, or there are more than one code word which is jointly typical with the output, then the decoder will simply either declare an error or pick a random message, or pick message 1 by default or something like that. So we can say declare an error or pick a random message. Okay? So basically the decoder goes as follows. It observes the sequence Y, has a big table of all possible jointly typical pairs. Given Y, find if there is a unique code word in the code book, which is jointly typical with Y, if this exists, output the corresponding index. If this doesn't exist, pick a random index or declare an error. At the end, it's going to be the same. So we want to analyze the probability of error averaged over this ensemble of randomly generated codebooks. So this can be written. We use the overline notation. You see, overline notation here, this means ensemble average. So this is not the probability of error of a specific coding system. This is the probability of error averaged over the ensemble of all possible randomly generated codes defined before. So this will be simply the sum over all possible codebooks of the probability of generating codebook C times the probability of error of codebook C. So this is the average probability of error over the messages. So there are two averages. It's average probability of error over the messages and averaging over the codebook so that we get P bar, the ensemble average. So this term is the same as we have defined before when we introduce average probability of error, if you remember. So yeah, this is this term. So it's the sum over all messages of the probability of error given message M, and then divide by the number of messages. So we go like that. So we have here the expression for the average probability of error. Then we can simply exchange these two sums, summing over the messages outside and averaging over the random codebook inside. And then we see that when we average over all possible randomly generated codebooks, and those codebooks are generated IID, it means that given a table, every permutation of the rows gives you exactly the same probability. So it means that we can basically shuffle the messages as we want. It turns out that this term here, since we sum over all possible codebooks, is independent of index M, because there is a symmetry. For every codebook with a certain mth row, any permutation of the row, you can put this mth row in the first position and you will have the same probability. So it means that without loss of generality, we can fix small m equal to 1 and consider the inner term like this. And at this point, this external sum here goes away because we are summing over all m, and then we are divided by the number, and the inner sum is a constant with respect to m. So at the end, we have our ensemble probability of error is simply averaging with respect to all possible codebooks the probability of message error given that message 1 is transmitted. And this can be written in this way. It's simply the probability that a random, the decoding function, so the joint typicality test applied to random yn is different from 1, given that 1 is transmitted, when, of course, the underlying distribution here, you have to think about this. What is the underlying joint distribution in this problem? Well, we have a random sequence that we call x1, which is, say, the random first row of this of the code book that determines yn through the correct transition probability. And then we have many other random sequences that are all the other code words. Those code words, let me circle them in blue, those other code words are independent of x1, and therefore they are independent of y, because those are independently generated other rows of this random table. So we have here that x1 and y have the joint probability distribution. Actually, let's write it this way. Sorry. Yeah, let's write it in the following way. The joint distribution of x1 and y is the correct joint distribution of xn, yn, which is pxn, pyn given xn. And the other code words here are independent of y, so the joint distribution of any other of these code words and y is the product of the marginals, because x2n or x3n, all the other x's, are independently generated from x1, because the random codebook is generated IID, and therefore they are independent of y, so they have the same marginal distributions of x and y, but the joint distribution is the product of the marginals, is not the true joint distribution of input and output of the channel. Okay, so this is the picture underlying, say, the probability structure underlying this probability, right? And now we are going to analyze, compute this probability under this probability model. Okay, so we define the error event as the event that the decoder chooses something that is not 1. Okay, and this event is inside the union of two events. Event E1 is the transmitted code word xn1 and the corresponding output y are not jointly typical. If they are not jointly typical, well, the joint typicality decoder will not find the right index, and therefore it will just pick a stupid index, so we can count this as an error. The other event is that there exists some other m different from 1, such that x and m and y are also jointly typical. And in this case, it means that, well, either this other m is unique and then it will be chosen, but it's not 1, so we make an error, or both 1 and this other m are jointly typical, so there is no unique index, and again, we can count this as an error. Okay? So by the union bound, we have that our probability of error is upper bounded by the sum of these two probabilities. Probabilities of the event E1 plus probability of the event E2. And now we consider them separately. For E1, we notice that, as I said before, x, n1, and y are jointly distributed according to the joint distribution px, py given x. So we know that long sequences generated according to a certain joint distribution are jointly typical, with probability going to 1 as n going to infinity, so we can conclude immediately, essentially by the law of large numbers, that the probability of E1 goes to 0 as n goes to infinity, which means we can make this probability as small as we want for sufficiently large n. Let's analyze the second case, the second error, so E2. So E2 is the probability that for some n different from 1, the randomly generated sequence x and m and yn which are distributed as the product of marginals, are jointly typical. And this is exactly the setting of the packing lemma. We have a set of random vectors individually distributed according to a certain px. We have another random vector individually distributed according to a certain py. And we ask, what is the probability union over this set of random vectors? What is the probability that some of these random vectors is jointly typical with these other vectors when they are in fact independently distributed with a certain marginals, and the joint typicality is defined according to a certain joint distribution. So if you go back to the packing lemma, you see that this is exactly the case, and so we can directly upper bound this probability as the product of the number of vectors in the set. In principle, it should be 2nr minus 1, because we take all the code words but m equal to 1, but you know, exponentially this minus 1 is irrelevant, and in addition we go after an upper bound, so we can simply forget this minus 1 is irrelevant. So the size of the set, and then we have here the probability that two random vectors individually distributed according to the marginals but independent are in fact jointly typical. We know that this goes to 0 as 2 to the minus n times the mutual information minus a small quantity. So we conclude that the first term, PE1, can be made smaller than epsilon for sufficiently large n. This bound, this exponential bound, can also be made smaller than epsilon for sufficiently large n whenever the rate satisfies this inequality, because it means that the exponent is negative, and therefore I let n large, I can make this exponential as small as I want. So overall, we conclude that the probability of error can be made smaller than 2 epsilon, where epsilon is an arbitrary quantity, so as small as I want for sufficiently large n. So this proves the existence of at least one deterministic sequence of codes that perform not worse than the ensemble average. There is an S missing here. For any n, there exists at least one code that performs not worse than the ensemble average. So this proves the existence of a sequence of codes of rate r and increasing block length whose error probability can become as small as we want for sufficiently large n. Second, if you remember, we have chosen px in an arbitrary fashion, and we find this condition. So now we want to make this term as big as possible in order to have this condition as, you know, as non-restrictive as possible, so in order to consider the largest possible set of achievable rates, so we can maximize the mutual information with respect to px, and this condition will remain true. So basically, this proves the achievability of every rate r less than max over p mutual information, because the penalty delta here also can be made as small as we want by making epsilon small, right? So we can go as close as we want to this limit, and since the capacity is the supremum, well, that's essentially is like the least upper bound to the achievable rates we have found, right? Which is exactly the definition of supremum. At this point, so let's call this this thing called C from the theorem, right? there is only one little gap in the proof, is that normally we define achievability in terms of maximal probability of error, but here we have analyzed the ensemble average of the average probability of error. So it's a slightly weaker notion of probability of error. So this achievability can be made stronger, so going from average to maximal probability of error with an argument that is called expurgation. So the idea of expurgation is the following. So fix epsilon greater than 0 and let C star n to be that code, fixed code, that we have proven to exist, such that the average probability of error is less than epsilon, and the rate is greater than C minus delta epsilon. Okay? So at this point, we can take all the code words of this fixed codebook C star and sort them by conditional message error probability. So without loss of generality, we can say, we can resort the messages and order their conditional error probabilities in this way, right? So we will have that 1 is the luckiest message because it has the smallest probability of error, 2 is the second luckiest, and then the last one is the highest, okay? Good. So the idea is that we can take the best half of this code book. So the best half is taking, the 2 to the n r minus 1 best code words, and then throw away the 2 to the n r minus 1 worst code word. And the claim is that the maximal probability of error of the best half must be, so max I less or equal than 2 to the n r minus 1 of p e I of c n star must be less or equal than 2 epsilon. Why is that? Because if this was not true, then all these code words, because they have bigger error probabilities, altogether they would contribute for more than epsilon to the average error probability. If you imagine that all these terms are, half of the terms are bigger than 2 epsilon, you sum them together and you get 2 to the n r minus 1 times something that is bigger than 2 epsilon. So let's write here 2 epsilon, right? Then you define, you divide by 2 to the n r, and what you get is epsilon. So if all these terms were 2 epsilon, just the half of these would contribute for the average equal to 2 epsilon. So you see, this means that the maximum here, the maximum of the best half, cannot be more than 2 epsilon. So at the end, this proves the following. Taking the best half of the code words, we get a new code book that I called C star tilde that contains only half of the code words, but its maximal probability of error is smaller than 2 epsilon. Now, what is the rate of this code book? Well, the rate of this code book will be 1 over n times log of 2 nr minus 1, which is nr minus 1 divided by n, which is r minus 1 over n. So here, the rate is almost unchanged because n is very large, r minus 1 over n is almost r. So the rate is essentially, again, goes as close as we want to r. The probability of error, the maximal probability of error, is less than 2 epsilon, but epsilon is an arbitrarily small quantity, so 2 epsilon is also an arbitrarily small quantity. So this proves that there exist codes with rate as close as we want to capacity, because we have chosen R to be greater than C minus delta epsilon, and now we have a new rate R prime equal to R minus 1 over n. So at the end we have that this R prime is greater than C minus delta epsilon minus 1 over n, right? And this is also as close as we want to see, because this goes to 0 with epsilon, this goes to 0 with n, and the maximum error probability to epsilon also goes to 0 with epsilon. So we can pick epsilon small as we want, n large as we want, and we have proven the achievability also for the maximum probability of error. Okay? So this concludes the direct part, because we have shown the existence of sequences of deterministic codes for increasing block length and rate up to capacity, for which the probability of error can be made as small as we want as n increases. Okay? But that's not the end, because we have also to prove the non-existence in order to show that C is in fact the capacity, so coincide with the operational definition of capacity. So in order to prove that there exist no codes with rate greater than C and arbitrarily small probability of error, it is in fact more convenient to assume that we have a family of codes, non-random, somebody, a genius, give us this family of codes, with rate R and block length n, such that their probability of error vanishes as n goes to infinity. And by the way, here we can even relax a little bit. Instead of considering maximal probability of error, for the converse, we can consider average probability of error, which is a relaxed constraint. So if no code exists with the vanishing average probability of error, then for sure no code exists with vanishing maximal probability of error. So for the converse, we can also relax a little bit the condition for achievability from maximal probability of error to average probability of error, and still get the converse we want. So we assume that these codes exist, and then through a series of inequalities, we will prove that necessarily if such code exists, then the rate cannot be bigger than C. Okay? And so where C is that maximum mutual information that we have seen before. So this is indeed the way to prove the converse, and we will prove the converse using Fan inequality, which is again this link between probability of error in decision making and conditional entropy. Okay? So we have to consider here that all the probabilities, the probability structure that we are considering here for analyzing these probabilities and writing down these mutual informations that we will do in a moment, is induced by the given code. So in other words, we have messages M are uniform over the message set. The code words xn is simply therefore uniform over Cn, where this is a given codebook. We don't know how this codebook is constructed, it's given to us. The only thing we know is that probability of error vanishes as n goes to infinity. And the output yn is distributed according to product from 1 to n, py given x, yi given xi. So it's the conditional probability distribution given message M. So given code word, say the code word X and therefore message M. Okay. So in other words, given a code book and given a uniform probability of messages and given the transition probability of the channel, this induces what we call a joint message input and output n-letter distribution. N-letter distribution because we consider vectors of length n. Now we can write the following. N times R is logarithm of the size of the message set. Since the messages are uniform, this is equal to the entropy of the messages. Now we can add and subtract these conditional entropy. Notice that M is what we want to estimate at the decoder. Y, N, is what is the observation. So that's precisely that conditional entropy that appears in Fano inequality. When we have a decision making, the decoder wants to estimate M from Yn. And then the difference between these two terms is simply the mutual information between the message and the output sequence. And these conditional entropy by Fano inequality can be upper bounded by 1 plus N times probability of error times R. And why is this? Because log of the message set is simply NR. Okay, so that's the usual, remember Fano inequality would give this conditional entropy is less or equal than probability of error times log of the size of the messages, which is NR, plus the binary entropy function of the probability of error. But this is always less or equal than 1 because it's a binary entropy function, so we use 1 to make it even simpler. Then we can apply the, on this term, we can apply the chain rule of mutual information. We have M is a random variable, Yn is a vector. We can develop this mutual information with respect to y, and so this is just, we get this term, which is simply applying the chain rule. And here, if we collect n in front, here we have, n times 1 over n plus p e l r. Now, when n becomes large, 1 over n goes vanish, and pe of n by assumption vanish. So this whole quantity here is a vanishing quantity with n, and we call it epsilon n, where epsilon n goes to 0 as n goes to infinity. Notice that this is the product of n times epsilon n. N times epsilon n may not go to 0. In fact, it does not, because n times 1 over n is 1. So this will be at most order of 1. But when we collect n in front, what multiplies n, so this epsilon n, is vanishing. Okay? Good. So now what we can do is simply augment each of these terms by essentially using the chain rule in reverse mode and replacing this term by this mutual information. That's easy to see. Then we can notice that if we add here xi, so the ith letter of the code word. Now this code word is a function of m, so adding xi here has no impact, because you can add whatever function or whatever is already there. You will not change the mutual information. But now we see that because of the memoryless property, yi is independent of everything else, message and the past y's, if condition on the current input. So if we develop this term by the chain rule, we have that this is mutual information of xi, yi plus mutual information of m yi minus 1 and yi given xi, but given xi, these and these are independent, so this term is 0. So we have that this is just mutual information of xi, yi. Okay? So now what we can do to conclude is that, so what are these terms? These are the mutual information of the ith marginal joint p yi comma so xi yi induced by the n letter joint distribution. Okay, so I said before that the uniform probability of the messages, the codebook, which is fixed, and the channel transition probability determines a joint n-letter distribution. If we marginalize with respect to the ith component, we get a joint distribution of xi, yi, and this marginal distribution of xi, yi determines this mutual information. We don't really know how xi is distributed. Why? Because it depends on the codebook, and here we are given a deterministic codebook, so we don't know. We cannot make assumption. It's not like uniform or whatever. We cannot optimize. It cannot. But what we know is that if each of these terms, for whatever joint distribution, these terms are upper bounded by C, because C is the maximum. So for any joint distribution in the ith marginal, this mutual information is less or equal than the max over px of this. Just because here we are maximizing over the input distribution, while for the term here marked in orange, this is for a given marginal distribution of xi that depends on the codebook that we don't know, but certainly it cannot be larger than the maximum. So we can upper bound each of these terms. Oopsie, you can upper bound each of these terms with C. So now we end up with, wrapping up all this argument, we end up with the inequality that if such code exists, then nr must be less or equal than nc plus n epsilon n. We divide everything by n, we find r less or equal than c plus epsilon n. Since epsilon n goes to 0, we conclude that if such family of code exists, then r must be less or equal than c. Okay? So, conclusion is, no code with vanishing probability, no sequence of codes with vanishing probability of error can exist for rate greater than c. Because we have assumed that such sequence exists, and this concludes that the rate must be less or equal than c. Okay? So that's the end of the converse part, and so since converse and achievability coincide, we have proved achievability for all rate arbitrarily close to but not larger than c, and non-existence for all rates greater or equal than c. Then we have determined that this maximum mutual information that the theorem says, call it c, is in fact the capacity of the channel, because we have given like an operational meaning to this quantity max over px of mutual information xy. Okay, So this is really a fundamental theorem and also fundamental steps in the proof of achievability and converse that will be used in many other. It's like a pattern. It's a proof pattern that can be replicated to other examples or to other cases. Very good. So I guess we can finish here for this part, and in the third part we are going to finish up this chapter with some more results.